In the grand, silent theater of the cosmos, where stars are born and die in cycles of unimaginable timescales, humanity has built its own set of eyes. They are the tireless sentinels, the robotic telescopes that scan the deep dark, night after night, their digital consciousness sifting through an avalanche of data, searching for the unscripted. For the most part, they find the familiar, the predictable waltz of asteroids in their designated belts, the faint ghostly glow of a distant nebula, the occasional fiery streak of a meteor burning up in our atmosphere. It is a work of cosmic bookkeeping, essential but often routine. But on a quiet Tuesday in the not-so-distant future, an anomaly flickered into existence. It was not a dramatic burst of light, not a cataclysmic explosion, but something far more subtle, and therefore far more intriguing. Deep within the digital stream of the Asteroid Terrestrial Impact Last Alert System, the ATLAS survey in Hawaii, a new point of light was flagged. It was faint, unassuming, and moving with a purpose that, at first, seemed entirely ordinary. The initial designation was routine, another letter and number combination added to the ever-growing catalogue of celestial wanderers. Astronomers around the world, notified by the automated system, turned their own instruments toward the newcomer. They expected to see a comet, perhaps, on a long elliptical journey from the Oort cloud, the sun's most distant reservoir of icy bodies. They anticipated the gentle formation of a coma, a soft halo of gas and dust sublimating as the object drew nearer to the warmth of our star. They prepared to plot its trajectory, to calculate its orbit, and to predict its path through our solar system before it would inevitably swing back out into the lonely darkness from whence it came. For a few days, everything proceeded as expected. The object, christened 3I divided by Atlas, grew steadily brighter, just as a comet should. But then, the data began to whisper a different story. The models, so reliable and precise, started to diverge from the reality being observed. The discrepancy was tiny at first, a rounding error, perhaps a slight miscalculation, but it persisted, and it grew. The object was not slowing down as it should. In fact, it was doing the opposite. It was accelerating, but with a gentle, continuous push that defied explanation. There was no visible outgassing, no tail of dust and gas to act as a natural rocket engine. It was moving as if guided by a force unseen, a silent engine running in the vacuum of space. The routine observation had become a profound enigma. This was not just another rock or a ball of ice. This was something else. This tiny, unassuming point of light, this ghost in the machine, was beginning to challenge our fundamental understanding of what could wander between the stars. It was a messenger from the void, but what message was it carrying? And more pressingly, what was pushing it? That question, what was pushing it, reverberated through the digital corridors and quiet control rooms of observatories across the globe. In the precise, elegant mathematics of celestial mechanics, there are few unknowns. An object's path is a dance choreographed by gravity, primarily the immense gravitational pull of the sun, with subtle nudges from the giant planets. For an object like 3I divided by Atlas, its trajectory should have been as predictable as the sunrise. The deviation, this gentle but persistent acceleration away from the sun, was a violation of that choreography. It was a note played out of tune in the cosmic symphony. Science, however, is not a practice of accepting mystery, but of dismantling it. And there was one well-understood, perfectly natural explanation for such a push. Cometary outgassing. A comet is not merely a rock, it is a dirty snowball, a primordial relic forged in the freezing outer darkness of a solar system. As it ventures closer to a star, the ice beneath its surface warms, turning directly into gas in a process called sublimation. This gas, erupting from fissures and vents on the comet's surface, acts like a series of tiny natural rocket thrusters. The force is minuscule, but in the frictionless vacuum of space, over weeks and months, it is enough to tangibly alter the comet's path, to give it that extra, non-gravitational push. This was the most logical, the most Occam's razor-approved explanation. 3I divided by Atlas had to be a comet, and so the great eyes of Earth turned their gaze upon it with a new mission, to find the thrusters. The hunt for the coma began in earnest. The most powerful instruments humanity has ever built were commandeered. The James Webb Space Telescope, floating silently at its Lagrange point 1 million miles from Earth, pivoted its golden mirrors. Its infrared senses, capable of detecting the faintest warmth from the most distant galaxies, were perfectly suited to find the telltale glow of water vapor, carbon dioxide, or carbon monoxide, the standard ingredients of a comet's breath as they were warmed by the sunday. Astronomers booked time on the Very Large Telescope in Chile, its 4 giant units working in concert as a single light-devouring entity. They searched the visible spectrum for the faint, diffuse cloud of dust and gas that should be enveloping the object's core. Radio telescopes, from the ALMA array high in the Atacama Desert to the Greenbank Telescope in West Virginia, listened intently, straining to catch the specific radio frequencies emitted by hydroxyl radicals, the broken-down remnants of water molecules, the undeniable signature of a bleeding comet. Days turned into weeks, and the results that trickled in were as unanimous as they were unsettling. Nothing. There was no infrared signature of sublimating gas. There was no visible cloud, no faint halo of dust. The radio spectrum was utterly silent. The object was as clean, as inert, as a piece of sterile rock. It was a ghost ship sailing against the current with no sails and no engine. The paradox deepened into a chasm. Here was an object with a cometary effect, the acceleration, but with absolutely zero cometary cause. The data was checked, double-checked, and triple-checked. The instruments were recalibrated, the models were run again and again, but the conclusion was inescapable. The object was being pushed, yet nothing visible was pushing it. It was in this atmosphere of profound scientific confusion that the memory of another ghost began to surface. A name was whispered in online forums, then spoken in hushed tones during video conferences between international teams. Oumuamua, the first interstellar object ever detected passing through our solar system, discovered in 2017. Its name, Hawaiian for scout, was a fitting tribute to its mysterious origin. Oumuamua was a statistical inevitability that, when it finally arrived, was stranger than anyone had imagined. It was small, dark, reddish, and highly elongated, tumbling through our system on a trajectory that could only have come from the vast emptiness between the stars. But its most baffling characteristic, the one that ignited years of fierce debate, was that it, too, was accelerating. Just like 3I divided by Atlas, it was being pushed by an unseen force, a gentle nudge away from the sun that could not be explained by gravity alone. And just like 3I divided by Atlas, a meticulous search revealed no coma, no outgassing, no tail. It was the exact same riddle, written in a different hand, arriving on our cosmic doorstep years later. The scientific community had fractured over Oumuamua. Some proposed it was a new, unknown type of natural object, perhaps a nitrogen iceberg chipped from a Pluto-like world in another star system, its outgassing invisible to our telescopes. Others suggested it was a hydrogen iceberg, an even more exotic and theoretical proposition. And one prominent astronomer, Avi Loeb of Harvard University, dared to voice the most extraordinary hypothesis of all, that Oumuamua's strange acceleration was the result of solar radiation pressure pushing against an object that was extremely thin and light for its size. An object, he proposed, that could be an artifact of an extraterrestrial technology, a solar sail. The idea was met with immense skepticism, but the mystery of Oumuamua was never definitively solved. It was moving too fast and was detected too late. It swung around the sun and shot back out into the interstellar void, taking its secrets with it. It became a cosmic what if, a single tantalizing data point that hinted at a universe far stranger than our neat categories allowed. But now, here was 3I divided by Atlas. It was not a fleeting glimpse. It had been found much earlier in its approach, its trajectory tracked with far greater precision. It was as if the universe had decided to run the experiment a second time. The feeling of déjà vu among astronomers was palpable. This was not just another puzzle. This was a chance at redemption. It was an opportunity to finally answer the questions that Oumuamua had left hanging in the void. Was this a new, bizarre class of natural interstellar object that our theories had failed to predict? Or was history repeating itself in the most profound way imaginable, sending us another piece of a puzzle whose final picture could reshape our entire understanding of our place in the cosmos? To stand before such a paradox, an effect without a visible cause, is to stand at the very frontier of knowledge. In these moments, Science does not retreat into confusion, but instead returns to its most fundamental principles, re-examining the very grammar of the universe to see if a rule has been overlooked. The grand, declarative statement of cosmic motion has always been gravity. It is the force that sculpts galaxies, that holds planets in their orbits, that dictates the fall of an apple and the path of the moon. For centuries, our understanding of the heavens was built upon this single, elegant law. It was a universe of celestial clockwork, wound by gravity and left to run its predictable course. But the cosmos, we have learned, is a place of far greater subtlety. Gravity is the dominant voice, the deep bass note that underpins reality, but it is not the only voice in the choir. There are other forces, fainter and more ethereal, that can influence an object's journey through the void. These are the non-gravitational forces, a term that sounds technical but simply describes any push or pull that isn't born from the warping of space-time by mass. We have already met one of these, the outgassing of a comet, a form of natural rocketry. But with that possibility seemingly ruled out for three, divided by Atlas, we must look to an even more delicate, more pervasive force, one that is born from the very heart of our Sunday. We must consider the pressure of light itself. It is a concept that feels alien to our terrestrial experience. We do not feel the press of the sunshine on our skin, only its warmth. Light, in our everyday lives, is an intangible medium of perception, the carrier of color and shadow, not a physical force. But this is a limitation of our scale. At the quantum level, light is composed of a ceaseless river of particles called photons. Each photon is a massless, indivisible packet of energy, a messenger sent from the heart of a star, traveling at the ultimate speed limit of the universe. While they have no mass, they do possess momentum. And when a photon strikes a surface, it imparts a tiny, almost infinitesimal push, like an impossibly small billiard ball striking a target. A single photon's impact is negligible. A billion photons are still negligible. But the sun does not emit a billion photons. In a single second, it unleashes a torrent of energy so vast that it outshines all the lights ever made by humanity combined. It is a flood of photons, a continuous, unrelenting cascade washing over every square inch of our solar system. This ceaseless torrent creates a form of pressure, a delicate but persistent force known as solar radiation pressure. Imagine it as a wind, not a wind of air, of moving atoms and molecules, but a wind of light, a ghostly current flowing outward from the sun in all directions. Now imagine different objects caught in this wind. A dense, solid asteroid, a mountain of rock and metal kilometers wide, is like a great stone boulder in a gentle breeze. It feels the push, but its own immense inertia, its sheer massiveness, makes the effect almost immeasurable. The boulder does not move. The force of gravity on that asteroid is millions of times stronger than the gentle pressure of sunlight, and so its path is dictated by gravity alone. But what if the object in this wind was not a boulder? What if it was a leaf? Or better yet, a sail. A vast, thin sheet with a huge surface area but very little mass. That same gentle breeze, which failed to budge the boulder, would now catch in the sail. It would push it, gently at first, but continuously. In the frictionless expanse of space, where there is no air resistance to slow it down, that constant, tiny push would cause the sail to accelerate. It would move faster and faster, driven by nothing more than the power of starlight. This is the principle behind the human concept of a solar sail, a theoretical spacecraft propelled by this very force. Here, then, is a potential solution to the riddle of 3I divided by Atlas. Here is an engine that is both silent and invisible. The ghostly acceleration that defied explanation could be the work of this solar wind. If this were true, it would mean that 3I divided by Atlas is not a cosmic boulder. It must be a cosmic sail. It must possess a set of physical characteristics that are radically different from any natural asteroid or comet we have ever witnessed. To be so profoundly affected by the gentle pressure of sunlight, it would need to have an extraordinarily large surface area, combined with an incredibly low mass. It would have to be, in essence, very thin, very light, or perhaps both. It could not be a solid, tumbling, potato-shaped rock. It would have to have a shape and density that make it exceptionally susceptible to being pushed by photons. The mystery, therefore, has transformed. The question is no longer simply, what is pushing 3I divided by Atlas? The question has become far more profound, far more specific. What kind of object has a structure that allows it to catch the wind of light? In asking this, we are no longer just observing a strange rock in the sky. We are beginning to infer its very nature, its form, and its substance, based on how it dances in this unseen current. And it is this very line of reasoning that forces us to look back, to remember the first time such an unsettling dance was witnessed, to revisit the story of the first scout from the stars. This line of reasoning that an object's strange motion could betray an even stranger nature is not a path we are treading for the first time. To fully comprehend the seismic implications of what 3I divided by Atlas represents, we must cast our minds back less than a decade, to a moment in 2017 when the universe first sent us a riddle wrapped in an enigma. It arrived unannounced, a faint streak of light detected by the Pan-STARRS telescope, also in Hawaii. Its trajectory was immediately flagged as extraordinary. It was not bound by the sun's gravity. It was moving too fast, on a path so steep and open a hyperbolic orbit that it could only have come from one place, the vast dark sea of interstellar space. It was the first confirmed visitor from another star system. We named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, or scout. The name was poetic, but it would prove to be an almost prophetic understatement of the object's profound weirdness. From the very beginning, Oumuamua defied our neat classifications. Its light curve, the way its brightness flickered as it tumbled through space, suggested a shape unlike anything we had ever seen. It was not a roughly spherical asteroid or comet. The data implied it was exceptionally elongated, perhaps 10 times as long as it was wide, like a cosmic cigar, or perhaps a flat, pancake-like shard. It was dark, with a reddish hue, the result of eons of exposure to sterilizing cosmic rays on its lonely voyage between the stars. But its most confounding feature, the one that elevated it from a mere curiosity to a lasting scientific controversy, was its motion. As it looped around the sun and began its journey back out into the void, astronomers tracked its position with painstaking precision, and they found the ghost. Oumuamua was also accelerating. It was being pushed by that same gentle, unseen force, a persistent nudge away from the sun that could not be explained by gravity. Immediately, the scientific community focused its collective might on the object, searching for the logical cause, a cometary tail. And just as with 3I divided by Atlas years later, they found nothing. The Spitzer Space Telescope, one of our most sensitive instruments, stared at Oumuamua and saw no trace of the carbon-based molecules that should surround an active comet. There was no dust, no gas, no coma. The Scout was running a silent engine. This paradox split the astronomical world and ignited one of the most vigorous debates in modern science. On one side, researchers scrambled to find a natural explanation, however exotic. Perhaps, some proposed, Oumuamua was a nitrogen iceberg, a fragment broken off from a Pluto-like exoplanet, and its outgassing of pure nitrogen would have been invisible to our telescopes. Others suggested it could be a hydrogen iceberg, a theoretical object made of solid hydrogen that would also produce a transparent exhaust. These were ingenious ideas, born from a desire to explain the anomaly within the known laws of physics, but they required us to imagine new classes of celestial objects for which we had no other evidence. On the other side of this debate stood a smaller, more cautious, yet intellectually daring camp, most vocally represented by Professor Avi Loeb, then the chair of Harvard's astronomy department. He applied a starkly simple logic. If one has methodically eliminated all conventional explanations, and the unconventional natural explanations require inventing new physics or new types of objects, then one is obligated to consider the remaining possibility, no matter how profound its implications. Loeb pointed out that there was one explanation that fit all the data without deviation. The acceleration was a perfect match for the models of solar radiation pressure acting on an object with a very large area and a very low mass. Oumuamua, he argued, behaved exactly as a solar sail would. And because nature does not tend to produce vast, ultra-thin sheets of material, He concluded that we must seriously entertain the artificial hypothesis, that Oumuamua was a piece of extraterrestrial technology. He wasn't necessarily claiming it was a piloted ship, but perhaps a probe, a buoy, or even a piece of space debris from a distant, unknown civilization, a message in a bottle, not of words, but of physics. The hypothesis was, and remains, deeply controversial, but the debate was ultimately cut short by the unforgiving laws of celestial mechanics. Oumuamua was detected late, as it was already on its way out. It was a fleeting shadow. By the time the controversy reached its peak, the object itself was already far beyond the reach of our best telescopes, disappearing back into the interstellar night, taking its secrets with it. It left behind a legacy of unanswered questions, a single, tantalizing data point that hinted at a cosmos far more complex and perhaps far less empty than we believed. It became a ghost story astronomers told, a reminder of the limits of our observation. But now, with 3I divided by Atlas, the ghost has returned. This is not a fleeting glimpse. This object was detected early on its approach, its path tracked with far greater accuracy. The same impossible physics are at play, the same questions are being asked. But this time, the subject of our interrogation is not receding into the darkness. It is drawing closer. The universe, it seems, has presented us with the same riddle a second time, and this time, humanity has mobilized its watchmen, ready to give this new messenger the welcome it deserves. The shadow of Oumuamua, the ghost of a missed opportunity, now served as a powerful catalyst. The mystery of 3I divided by Atlas was no longer a quiet whisper in the halls of academia. It was a clarion call that echoed across continents, galvanizing the global scientific community into a state of unprecedented, coordinated action. The unspoken consensus was clear and absolute. This one would not get away. We would not be left with a decade of speculation and a handful of ambiguous data points. This time, we would bring the full, unblinking gaze of human ingenuity to bear on this silent traveler. What followed was less an astronomical observation campaign and more of a planetary immune response, a system-wide mobilization of our most advanced sensory organs, all directed at a single point of light in the celestial ocean. Time on the world's greatest telescopes, normally booked months or even years in advance, was cleared. Protocols for rapid, international data sharing, usually mired in bureaucracy, were activated with emergency overrides. It was a testament to our species' innate curiosity, a silent agreement that when the universe presents a question of this magnitude, our terrestrial rivalries and divisions seem suddenly insignificant. The strategy was a multi-pronged assault, an interrogation conducted across the entire electromagnetic spectrum. Each type of telescope was a specialist, tasked with asking a different, crucial question. First were the infrared sentinels, chief among them the James Webb Space Telescope. Floating in the cold darkness, its mirrors shielded from the sun's glare, its mission was to hunt for the faintest whispers of heat. It stared at 3I divided by Atlas, searching for the telltale glow of sublimating gases, hoping to definitively answer the comet question once and for all. A positive detection would solve the riddle in the most conventional way possible, but a negative result, a confirmation of cold silence, would be far more profound. Beyond merely detecting heat, the Webb's powerful spectrographs were tasked with dissecting the faint light, reflecting off the object's surface. Light is a messenger. Encoded within its spectrum are the chemical fingerprints of the materials it has touched. By breaking the reflected sunlight into its constituent colors, a rainbow barcode, astronomers could determine if it was made of rock, ice, metal, or something else entirely. The Webb was tasked with answering the most fundamental question, what are you made of? Simultaneously, the great optical observatories on Earth swiveled their colossal structures toward the visitor. From the high, arid plains of the Atacama Desert in Chile, the Very Large Telescope and the twin giants of the Keck Observatory in Hawaii began their vigil. Their objective was precision. As the Earth turned, they would pass the digital baton from one observatory to the next, ensuring not a single moment of the object's journey went unrecorded. They were not just taking pictures, they were meticulously measuring its brightness, photon by photon, constructing the most detailed light curve ever assembled for an interstellar object. They sought to map every flicker, every minute change in its reflectivity. From this data, they could deduce its rotation, its stability, and most importantly, gain a more refined understanding of its shape. Was it tumbling chaotically like a misshapen asteroid? Or was its rotation stable, perhaps even controlled? Was it a simple elongated shape? Or did its light curve betray a more complex structured geometry? Their task was to answer the second question: what is your form? And then there was the third front, perhaps the most evocative of all. The giant, ear-like dishes of the world's radio telescopes turned their attention away from distant pulsars and quasars and began to listen. The SETI Institute's Allen Telescope Array in California, a network of antennas designed for the express purpose of searching for extraterrestrial intelligence, began a targeted campaign scanning a broad range of frequencies. They were not necessarily expecting a greeting, a hello from the stars. They were listening for something far more subtle: the unintentional hum of technology, the stray radio waves, the data leakage, the background noise that any active piece of machinery might emit. It was the longest of long shots, but one that had to be taken. In concert with this passive listening, a more active approach was initiated. The most powerful radar transmitters on the planet, like the Goldstone Solar System radar, prepared to send out focused beams of radio waves to ping the object in a form of cosmic sonar. By analyzing the faint echo that returned seconds or minutes later, scientists could directly measure its size, its velocity, and perhaps, if they were incredibly lucky, even create a crude, ghostly map of its surface features. The radio telescopes were asking the most daring question: are you silent? And can we see you in the dark? For weeks, this global watch continued. Data, measured in petabytes, flowed from mountaintops and spaceborne observatories to supercomputers around the world. 1,000 minds, united by a single, unified question, worked to piece together the portrait of this enigma. The world held its breath, waiting. The preliminary analyses were complete, the error bars were checked, and the raw observations were translated into the language of scientific understanding. And the first fragments of the answer did not come from a photograph or a sound, but from the silent, coded language of light itself. The first definitive piece of the puzzle arrived not with a thunderous announcement, but as a series of graphs on a screen, the silent output from the James Webb Space Telescope. To the untrained eye, it was merely a jagged line, a plot of brightness against the wavelength of infrared light. But to an astronomer, this graph is a language, a Rosetta Stone for deciphering the cosmos. Every object in the universe, from a humble asteroid to a blazing star, has a unique spectral signature. When sunlight, a perfect blend of all colors, strikes an object, some of that light is absorbed by the materials on its surface, while the rest is reflected. The specific colors, or wavelengths, that are absorbed create a unique barcode of dark lines, an absorption spectrum. Water ice absorbs light in a specific way, silicate rock absorbs it in another. These are the familiar fingerprints of nature, signatures we have seen countless times on asteroids, planets, and moons throughout our solar system. They are the chemical alphabet with which the story of our cosmic neighborhood is written. The spectrum of 3I divided by Atlas was expected to show one of these familiar patterns, but it did not. As the data was processed and the final spectrum emerged, a profound and unnerving silence fell over the teams analyzing it. The expected barcode was missing. There were no significant absorption lines corresponding to water ice. There were no clear signatures for the complex carbon-based molecules, the tholins that coat so many outer solar system bodies in a reddish-brown soot. There were none of the telltale dips in the graph that would scream rocky, indicating the presence of olivine or pyroxene. It was as if the object was a blank page where a detailed history should have been written. The story of its origin, its composition, its very being was simply not there. The object was not made of anything we would consider natural, but the spectrum was not truly blank. It told a different story, one that was far stranger and more chilling in its implications. Instead of absorbing light at specific wavelengths, the object was exceptionally reflective across a broad, smooth range of the spectrum, particularly in the infrared. The line on the graph was not a jagged collection of natural fingerprints, but a smooth, gently rising curve. This is not the signature of a dark, porous, and uneven natural body. It is the signature of a surface that is unnaturally uniform and efficient at reflecting light. It is the signature of a mirror. When the scientists modeled the curve, comparing it to a library of known materials, the matches they found were not on the list of cosmic minerals. The best fits were found in a different library altogether, one of industrial materials science. The high reflectivity and the specific shape of the spectral curve were consistent with thin film metallic coatings, polished aluminum, titanium alloys, materials that are not found in their pure, refined states in nature, but are the product of advanced metallurgy and engineering. And there was more. Nestled within the smooth curve were subtle but distinct features, not of minerals but of long-chain molecules. The data hinted at the presence of synthetic polymers, carbon-based materials engineered for strength and thermal resistance. These were the fingerprints of technology. This was a paradigm-shifting moment, a quiet turning point in human history that took place on a computer screen. The debate was no longer purely about anomalous motion and the abstract physics of unseen forces. This was tangible. This was physical evidence. We were now looking at the chemical composition of an object from another star system, and it was telling us, in the unambiguous language of light, that it was not forged in the heart of a collapsing nebula or chipped from a primordial planet. It was constructed. The implications were staggering. If an asteroid is a geological sample of another world, then 3I divided by Atlas was something else entirely. It was an archaeological artifact. The focus of the global campaign now shifted with an intense new urgency. We had just learned what it was made of. The next piece of the puzzle, streaming in from the great optical telescopes on Earth, would tell us about its form, its structure, its shape, and it would prove to be just as unnatural as its composition. With the startling revelation of 3I divided by Atlas's unnatural composition, a silent declaration etched in the spectrum of reflected light, the focus of the global scientific endeavor intensified. If the light was whispering about refined metals and synthetic polymers, the next piece of evidence would begin to paint a picture of how these materials were assembled. This picture would emerge not from a direct image, but from the painstaking analysis of its fluctuating brilliance against the backdrop of distant stars. This is the art and science of the light curve. To truly appreciate the significance of a light curve, one must understand what it represents. Imagine a distant object tumbling through space. As it rotates, different facets of its surface catch and reflect sunlight back towards our telescopes. If the object is perfectly spherical and uniformly reflective, its brightness will remain constant. But most celestial bodies are irregular. They are potato-shaped asteroids, or elongated cometary nuclei, or icy moons pockmarked with craters. As these irregularly shaped objects spin, their visible cross-section changes. When a larger, more reflective side faces us, it appears brighter. When a smaller, darker, or edge-on profile is presented, it dims. By meticulously plotting these changes in brightness over time, astronomers can deduce an incredible amount of information. The object's rotation period, its axis of rotation, and critically, a strong inference about its overall shape. A rapid, irregular flicker might suggest a chaotic tumble. A slow, steady oscillation points to a stable spin. A dramatic swing from bright to bright again implies a highly elongated or very flat object. The optical observatories, from the towering domes of Mauna Kea to the high plateaus of Chile, poured their collective light-gathering power onto 3I divided by Atlas, recording its luminosity with unparalleled precision. The light curve that emerged was unlike anything commonly seen from a natural interstellar visitor. If Oumuamua's light curve had been a curiosity, its extreme elongation hinting at something unusual, then 3I divided by Atlas's was a profound declaration. It was not a gentle, chaotic wobble. It was a rapid, dramatic, and astonishingly consistent oscillation. The object's brightness plummeted by an extraordinary amount, sometimes by as much as 80% to 90%, before rebounding to its peak brilliance, all within a matter of hours. This was not the subtle dimming of a rocky body showing a slightly different face. This was the near disappearance and reappearance of a substantial amount of reflective surface. Such extreme variations in brightness could only be explained by one of two scenarios for a natural object. Either an extremely elongated, cigar-like shape, tumbling end over end, or a very flat, disc-like or plate-like object. However, the sheer magnitude of the brightness change, coupled with the previous spectral analysis indicating a highly reflective surface, pushed the interpretation firmly towards the latter. Imagine a vast, thin sheet of polished metal. When it faces you squarely, it glints with blinding intensity. But turn it edge on, and it becomes almost invisible, a razor-thin line cutting through the air. The light curve of 3I divided by Atlas behaved precisely this way. It suggested an object that possessed an extraordinarily high aspect ratio, its width or length vastly exceeding its thickness. It was a cosmic razor blade, or perhaps a cosmic mirror, slicing through the vacuum. Further sophisticated analysis of the precise timing and symmetry of the light curve added another layer of intrigue. The pattern was incredibly stable, not chaotic. This implied a fixed, rather than random, axis of rotation. A natural object, especially one so thin, might be expected to tumble erratically due to slight imperfections or collisions over eons. But 3I, divided by Atlas, spun with a seemingly controlled, almost engineered regularity. The stability of its rotation, combined with its high reflectivity and extreme flatness, began to form a cohesive, albeit astonishing picture. This was not merely an irregular chunk of rock or ice. This was a structure designed to present a large, flat surface to its environment. The implications of this shape, when combined with its refined metallic and polymeric composition, began to resonate with the earlier dilemma of its mysterious acceleration. What kind of object in a natural setting would be so flat, so thin, so reflective, and possess such an enormous surface area relative to its implied mass? None that we know of. Yet, these are precisely the characteristics one would engineer into a device designed to interact maximally with the solar wind, to be propelled by the pressure of starlight. The light curve was not just describing a form, it was describing a function. It was telling us with compelling certainty that this object was not merely adrift. It was designed to catch the solar breeze. The next phase of analysis, focusing on its trajectory and the precise force pushing it, would solidify this interpretation, transforming a hypothesis into an almost undeniable conclusion. The portrait of 3I divided by Atlas was now rapidly coming into focus, each new piece of data adding a brushstroke to a picture that was becoming increasingly alien. Its composition was not of nature, but of industry. Its form was not the random tumble of a cosmic rock, but the stable, reflective geometry of a manufactured sheet. The final and most crucial step was to connect these newfound physical properties back to the original mystery that had started it all: its silent, ghostly acceleration. This required moving from inference to calculation, from what the object looked like to what it was, mathematically. It was time to re-engineer its trajectory, to use the object's own motion as the final key to unlock its identity. Celestial mechanics is a science of exquisite precision. Armed with the continuous stream of positional data from the global network of telescopes, astronomers could plot the path of 3I divided by Atlas with an accuracy measured in mere kilometers, despite it being millions of kilometers away. On one side of their ledger, they had the universe, as it should be, a perfect gravity-driven trajectory calculated using the laws of Newton and Einstein. This was the path the object ought to have been following. On the other side, they had the universe as it was, the object's real, observed path through our solar system. The difference between these two paths, the subtle, ever-widening gap between prediction and reality, was the acceleration. It was no longer a mystery. It was now a number, a measurable quantity. By subtracting the force of gravity from the object's observed motion, scientists could precisely calculate the magnitude and direction of the push. They had, in effect, placed the ghost on a scale and weighed it. This was a remarkable achievement, but it was only half of the equation. Now came the crucial test. In a parallel effort, another team of physicists worked from the opposite direction. They asked, what would be the force of solar radiation pressure on an object with the properties we have just observed? The formula for this force is well understood. It depends on the intensity of sunlight at the object's location and two key characteristics of the object itself: its reflectivity and, most importantly, its area to mass ratio. The spectral data had already given them a strong estimate for its high reflectivity. The only major variable left was this critical ratio of its surface area to its total mass. So they turned the problem on its head. Instead of guessing at the ratio, they took the precisely measured push from the trajectory analysis and plugged it into the solar radiation pressure equation. Their goal was to solve for the area-to-mass ratio that would be required for the gentle wind of sunlight to produce the exact acceleration they were witnessing. The number that emerged from the supercomputers was the definitive, undeniable climax of the investigation. The required area-to-mass ratio was unlike anything ever recorded for a natural object. Asteroids and comets are dense, compact bodies. Their area-to-mass ratio is exceptionally low. 3I divided by Atlas, however, required a value hundreds, perhaps thousands of times greater. It was a number that described an object that was almost all surface and virtually no mass. An object that was not just thin but functionally two-dimensional in its interaction with the cosmos. It was the physical parameter of a sheet of aluminum foil, not a mountain of rock. This was the keystone. The moment when three independent lines of evidence, spectroscopy, light curve analysis, and astrometry locked into place. The light curve had suggested an object that was extremely flat. The trajectory analysis now demanded an object that was extremely light for its size. The two conclusions, derived from entirely different methods of observation, had converged on the exact same, physically impossible for nature solution. This was no longer a series of strange coincidences. This was a self-consistent, mathematically verified description. The object was being pushed by the sunlight because it was an enormous, thin, reflective sheet. Its unnatural motion was a direct and predictable consequence of its unnatural form and composition. The mystery of the silent engine was solved. The engine was the object itself, its very structure designed to sail upon the stellar breeze. With the physical evidence now laid bare, a coherent and terrifyingly elegant picture had formed. The scientific process demanded one final step, a rigorous and dispassionate examination of all possible explanations, from the mundane to the monumental, to see which could withstand the full weight of this new, extraordinary truth. Before we take the final, momentous step in this deductive journey, we must pause. Science, in its purest form, is an act of disciplined skepticism, most especially when confronted with a conclusion that could rewrite our understanding of the universe. Before embracing the extraordinary, it is our absolute duty to give the ordinary one last, powerful chance to explain itself. The weight of evidence, the unnatural composition, the impossible shape, the perfectly explained acceleration points overwhelmingly in one direction. But what if we are missing something? What if there exists, somewhere in the vast catalogue of cosmic possibilities, a natural phenomenon so rare and so bizarre that it can perfectly masquerade as a work of intelligence? This is the last stand of natural explanations, the final attempt to find a ghost in the machine that is not of our own making nor of anyone else's. The most persistent and plausible natural hypothesis, a spectre that haunted the analysis of Oumuamua, is that of an exotic comet. We have established that 3I divided by Atlas is not a normal comet, venting water vapor and dust. But could it be something else? Could it be a body composed of a substance whose outgassing is invisible to our instruments? Let us first consider the nitrogen iceberg theory. In the frigid outer reaches of a distant star system, a world not unlike Pluto could have been shattered, sending a shard of frozen nitrogen tumbling into the interstellar void. As this iceberg approached our sun, the nitrogen would sublimate, creating a plume of pure, transparent nitrogen gas. This gas would be difficult to detect spectrally and would create no dust. It would, in theory, produce a gentle, continuous thrust. It is an elegant idea, but it runs into a wall of hard thermal physics. The James Webb Space Telescope is not just a camera, it is one of the most sensitive thermometers ever built. The process of sublimation requires a tremendous amount of thermal energy. It would leave a distinct signature, either by dramatically cooling the surface from which the gas was erupting, or by the gas itself being warmed by sunlight into a faint but detectable infrared glow. The Webb saw neither. It observed a body in perfect thermal equilibrium, a surface that was passively reflecting sunlight, not actively engaged in the violent, energy-consuming process of shedding its own mass. The object was not breathing. So we push the theory to an even more exotic realm. the hydrogen iceberg. The idea is that in the coldest, densest regions of a molecular cloud, solid hydrogen could form and coalesce into a comet-sized object. Hydrogen gas is the most abundant and simplest element in the universe, and its outgassing would be utterly transparent. This seems for a moment like a perfect solution. But the problem here is one of structural integrity. A solid hydrogen iceberg is a profoundly fragile thing, held together by the weakest of molecular bonds. The eons-long journey through interstellar space would be a trial by fire. The constant bombardment of high-energy cosmic rays and the erosive effects of the interstellar medium would sublimate such an object from the outside in. It would be like trying to send a snowflake through a sandblaster. For such an object to not only survive the journey but also arrive with enough mass to be detected and to produce the observed acceleration pushes the boundaries of physical possibility to their breaking point. If the exotic comet hypothesis fails, what remains? Could 3I divided by Atlas be a natural shard of material of an entirely different kind? Perhaps not a comet, but a piece of cosmic shrapnel, a fragment from some cataclysmic planetary collision that just happened to be blasted into an incredibly thin, leaf-like shape. In the chaos of a planetary breakup, it is conceivable that a thin crustal layer could be sheared off. This shard, if made of the right reflective minerals, could then be pushed by solar radiation. Here, however, we move from the merely improbable to the realm of astronomical coincidence. We would have to accept that this random act of violence not only created an object with an area to mass ratio hundreds of times greater than any known natural body, but that this same object was also composed of refined metals and polymers, and that it also maintained a stable, rather than chaotic, rotation. It asks us to believe in a series of independent, wildly improbable events that all, by sheer chance, conspired to perfectly mimic a solar sail. Occam's razor tells us that the simplest explanation is usually the correct one. And here we must ask ourselves, what is truly simpler? To invent an entirely new class of natural object, whose formation mechanism is unknown and whose multiple, disparate characteristics must align through pure chance to create this effect? Or to accept a single explanation where all of these characteristics, its thinness, its composition, its stability, its motion, are not a coincidence at all, but are the necessary and interconnected features of a single, coherent design. The attempt to find a natural cause has led us to a place where nature itself must be twisted into unrecognizable shapes. The ordinary has been exhausted. It has failed to account for the evidence, and in its failure, it has left us no other choice but to turn and face the only hypothesis that remains, the one that has been waiting patiently in the wings all along. And so, we arrive at the precipice. The ladder of hypotheses we have so carefully climbed has led us here to a final rung. We have tested every conceivable natural explanation, from the conventional to the deeply exotic, and found each one wanting. Each theory, when held against the full, unyielding light of the combined data, has fractured. A nitrogen iceberg cannot explain the thermal data. A hydrogen iceberg struggles against the physics of interstellar survival. A randomly formed cosmic shard requires us to believe in a chain of coincidences so vast as to be functionally impossible. The intellectual honesty of the scientific method demands that when all plausible natural explanations have been systematically eliminated, we must turn our gaze to what remains, no matter how profound its implications. The time for speculation is over. The time for conclusion, based on the logical weight of the evidence, has begun. The artificial hypothesis now takes center stage, not as a wild guess, not as a flight of science fiction, but as the sole remaining theory that provides a single, coherent, and elegant explanation for every single observed fact. Let us now, for a moment, cease to see 3I divided by Atlas as a mystery to be solved, and instead view it as a piece of technology to be understood. Suddenly, the disparate, confounding pieces of the puzzle snap into a perfectly clear picture. Its composition, a blend of refined metals and synthetic polymers, is no longer strange. It is a hallmark of intelligent design, the choice of materials engineered for reflectivity, durability, and low mass. Nature does not produce such things, but engineering does. Its form, the extremely flat, sheet-like geometry inferred from its dramatic light curve, is no longer an improbable accident of cosmic chance. It is a fundamental design requirement. A sail, by its very definition, must be thin and possess a vast surface area to effectively catch the wind. Its stable, controlled rotation is no longer a curiosity. It is a necessity for attitude control, for keeping its surface oriented correctly to the incoming photons to maintain a stable trajectory. And most critically, its motion, the gentle, constant acceleration that started this entire investigation, ceases to be an anomaly. It becomes the object's very purpose. The numbers align with breathtaking perfection. The force of the push, so precisely measured from its trajectory, is exactly what is predicted by the laws of physics for solar radiation pressure, acting upon an object with the very area to mass ratio, the very reflectivity, and the very shape that our other instruments have independently observed. It is a moment of profound intellectual synthesis. The cause and the effect are unified. The object moves the way it does because of what it is. It is not a rock being mysteriously pushed. It is a sail sailing. The acceleration is not a secondary, unexplained feature. It is the primary function of the device. In this light, 3I divided by Atlas is not a freak of nature. It is an artifact whose every observable property is a logical consequence of its function. The principle of Occam's razor, which guides us to the simplest explanation, now points decisively in this direction. The simplest explanation is no longer one that requires us to invent new categories of comets or impossible cosmic collisions. The simplest explanation is that this is precisely what it appears to be, a device crafted by intelligence, designed to travel between the stars propelled by the light of the stars themselves. This is no longer an extraordinary claim requiring extraordinary evidence. We now have the extraordinary evidence. The question has shifted from, could it be artificial, to, what evidence could possibly refute this conclusion? The burden of proof has reversed. To argue for a natural origin now requires one to ignore the consilience of the data and to retreat into a belief in nested improbabilities. The case, however, was not yet closed. Science demands finality. It seeks proof that is not just compelling but irrefutable, and that final, definitive proof was on its way. A single snapshot that would transform this entire intellectual exercise into a new and permanent reality for all of humanity. The case was compelling, the logic a closed loop. For the scientists and astronomers who had lived with the data for weeks, the conclusion was already a near certainty. But for humanity, for the 7 billion minds watching and waiting, an inferential leap is not enough. To truly grasp a reality-altering truth, we need to see it. A graph, a number, a spectral line, these are the tools of the intellect. But it is the image, the photograph, that speaks to the soul. The final chapter of this investigation would not be written in the language of mathematics, but in the universal, unambiguous language of light. And so, the call was made to deploy the ultimate eye, a new generation of space-based observatory with a lens not of glass, but of computation, a system capable of achieving a resolution previously thought impossible. It was not a single telescope, but a symphony of them, a virtual observatory created by networking multiple spaceborne instruments together. Using a technique called very long baseline interferometry, they could synthesize a virtual mirror the size of the Earth's orbit, capable of discerning details that would blur into nothingness for any single instrument. The target, 3I divided by Atlas, was still unimaginably far away, still just a single, unresolved point of light. The task was akin to trying to read the inscription on a coin from 100 miles away. It required hours of painstaking observation, gathering photons one by one, and then weeks of intense supercomputer processing to correlate the data, to filter out the noise, and to reconstruct a single, coherent image from the faint signal. The world watched as the progress bar on the final image render crept forward, and then it was complete. The image that resolved on screens in control rooms from Pasadena to Darmstadt was not a dramatic, cinematic reveal of a gleaming starship. It was something far more subtle, more elegant, and infinitely more profound. The pixelated blob that had been the subject of so much debate dissolved, replaced by a definite form. There, against the black velvet of space, was a structure of impossible delicacy. It was a vast, gossamer-thin membrane, faintly iridescent and stretched taut, its surface area immense. At its center was a small, denser hub, a nexus from which the sail seemed to emanate. The edges were not the jagged fractal lines of a natural fracture. They were clean, geometric, exhibiting the unmistakable signature of a manufactured object, the perfection of a straight line, the deliberate grace of a curve. There were no lights, no windows, no visible propulsion systems other than the sail itself. It was a thing of pure function, simple, silent, and utterly, undeniably artificial. This was it, the definitive proof, the glimpse of truth. It was not a debate to be had or a theory to be argued. It was a fact to be witnessed. The image was released. A stunned silence fell over newsrooms, social media, and living rooms across the globe. There was no more room for doubt, no more refuge in exotic naturalism. The ghost had been photographed. The debate was over. The artificial hypothesis was no longer a hypothesis. It was a confirmed observation. 3I divided by Atlas, the third interstellar visitor ever detected, was an artifact. The mystery that had begun as a tiny anomaly in a stream of data, a single discordant note in the celestial symphony, had been solved. But in that solution, in that single silent photograph, 1,000 deeper questions were born. The search for what 3I divided by Atlas is had concluded. The journey to understand what it means was only just beginning. The image was the final word in a long and meticulous argument. The debate was settled. Humanity, for the first time in its brief and noisy history, knew with empirical certainty that it was not alone. The initial, global reaction was a tidal wave of every emotion imaginable: elation, fear, wonder, dread. The immediate questions were primal, instinctual. Are they coming? Are they hostile? What is their message? Our entire history of fiction, of dreaming about the stars, had prepared us for a dialogue, an encounter, an arrival. We were primed for an active intelligence, for a presence that would engage with us. But as the days turned into weeks, and 3I divided by Atlas continued its silent, passive arc through our solar system, a new and far more profound realization began to dawn. The artifact was not speaking. It was not maneuvering with any new intent. It was not reacting to our radar pings or our intense scrutiny. It was simply obeying the laws of physics, a ghost ship sailing a course set by starlight and its own intrinsic design, a course perhaps set thousands or millions of years ago. It was in this sustained, deafening silence that our perspective underwent a fundamental shift. We had been preparing for an encounter, but we were being presented with an artifact. We were braced to meet a messenger, but we had found a message in a bottle, one whose author was long gone. We realized we were not xenobiologists about to meet a new life form. We were cosmic archaeologists, standing at the entrance to the tomb of forgotten giants. This object was not a herald of an impending arrival. It was a relic, an echo. Perhaps it was a fragment of a much larger structure, a piece of a vast solar sail that propelled a long-dead probe on its journey of exploration. Perhaps it was a marker buoy, a technological remnant whose parent civilization has since vanished, succumbing to time or some catastrophe we cannot even imagine. It is not a ship, it is a shipwreck. This realization does not diminish the discovery, it deepens it. It transforms our relationship with the cosmos from one of potential conversation to one of profound reverence and historical inquiry. If you were to unearth a lost Roman aqueduct in a remote desert, your first question would not be, "Are the Romans coming?" It would be, "Who were these people? What did they dream? What story does this structure tell?" So it is with 3I divided by Atlas. We must now learn to ask a different set of questions. Not, "What do you want?" but "What were you for?" Not, "Where are you from?" but "What was the world that made you like?" This is the birth of a new science, cosmic archaeology, the practice of sifting through the silent debris of the galaxy to piece together the stories of those who came before. This single, silent object proves that the universe has a history beyond the merely geological and astrophysical. It has a cultural history, an industrial history. It tells us that we are not the first to look up at the stars and feel the urge to touch them, and it forces us to confront the possibility that the great silence we have been so puzzled by is not the sound of an empty room, but the sound of an ancient, sprawling museum after closing hours. This transition from biology to archaeology, from encounter to investigation, forces us to confront the most persistent and humbling question of our scientific age, the Fermi paradox, the great silence. For generations, this question has echoed in the cathedral of human thought, a paradox born of two simple, powerful, and seemingly irreconcilable truths: the sheer statistical probability of life in a galaxy of 400 billion stars, and the profound, unnerving silence that greets our every attempt to listen. Given the age of the universe, there has been ample time for countless civilizations to arise, to master technology, to expand across the galaxy. So, as the physicist Enrico Fermi famously asked, "Where is everybody?" We have aimed our great radio dishes at the heavens, listening for a signal, a beacon, a single, structured whisper in the cosmic static. And for a century, the answer has been nothing. But the discovery of 3I divided by Atlas suggests a radical and transformative possibility: that we have been asking the right question, but we have been listening for the wrong answer. Our search has been predicated on a deeply anthropocentric assumption: the assumption that advanced civilizations would be loud in the way that we are loud. We, in our technological infancy, shout with radio waves. It is our primary means of long-distance communication. We have naturally assumed that any other intelligence would do the same, that the galaxy should be humming with a network of broadcasts, an interstellar internet of chatter. 3I, divided by Atlas, challenges this premise at its very core. It suggests that the evidence of intelligence might not be a shout, but a whisper, not a radio wave, but a physical artifact. The universe, it seems, has not sent us a text message, it has sent us a potsherd. In this new light, the great silence is not an absence of evidence, but a different kind of evidence. Perhaps the age of radio communication is an incredibly brief, fleeting moment in the lifespan of a civilization. Perhaps it is a noisy, primitive phase one quickly outgrows, abandoning it for more efficient, more subtle, or perhaps purely biological or quantum-entangled forms of communication that are utterly invisible to us. What, then, would survive the deep time between the rise of one civilization and the next? What endures for 1,000,000 or 100 million years? Not the ephemeral energy of a radio broadcast, which dissipates and weakens with every light year it travels. What endures are the bones, the structures. The things built with such robust materials and on such a grand scale that they can withstand the relentless erosion of eons. The great silence, then, is not the sound of an empty universe. It is the sound of time itself. It is the quiet hum of a cosmos where the lifespan of a technological civilization may be but a flicker. And the gulf of years separating those flickers is an ocean of silence, across which only the most durable relics can drift. This reframes the famous Great Filter theory, the idea that some obstacle prevents life from becoming interstellar. Perhaps the filter is not a single dramatic cataclysm. Perhaps the filter is simply time. Civilizations rise, they create, they explore, and then they fade, they transcend, or they die. And their legacy, their only enduring testament, is the silent flotsam and jetsam of their ambition cast out into the galactic sea. 3I, divided by Atlas, is the first piece of that flotsam to wash upon our shores. This does not make the universe a graveyard, necessarily. It makes it an archaeological site of unimaginable scale. It suggests that we are not the first, we are simply the next. We are the inheritors of a cosmos that has been lived in before, a home filled with the silent furniture of those who came before us. This discovery, therefore, does not truly cure our cosmic loneliness. It transforms it into something deeper, more poignant. We are no longer children crying out in a dark and empty house. We are explorers who have stumbled upon an ancient, abandoned city. There is a profound sense of connection in knowing that others walked these paths, that other minds looked out upon this same universe and were moved to build and to reach. But there is also a new, more profound sense of solitude in the deafening silence they left behind. Our search for intelligence must now evolve. We have been like men listening for whale song, and we have just found a fossilized whalebone. We must now begin to search not just for the songs, but for the bones. Our quest is no longer just to listen for a greeting, but to look for the silent, majestic ruins of the civilizations that came before. And so, we find ourselves at the end of one journey, and at the beginning of another, far grander one. The discovery of 3I divided by Atlas, this silent messenger from a forgotten age, does not crown humanity as the victors of the cosmos. It does the opposite. It gently but irrevocably humbles us. It places our entire existence into its proper, breathtaking context. All of our history, our empires and our art, our science and our wars, our love and our sorrow is but a single, fledgling sentence in an epic poem that has been in the writing for billions of years. We are not the authors of this story. We are simply the newest characters to be written into its pages. The universe we now understand is not just a collection of stars and planets. It is a museum of stories, a library of past ambitions, and we have just found the first artifact from a world that is not our own. The knowledge that others have walked this path, that other minds have gazed upon their own suns and dreamed of reaching out, does not diminish our own achievements. It ennobles them. Our own primitive probes, the Voyagers, carrying their golden records into the interstellar dark, are no longer a lonely shout into an empty abyss. They are our first tentative contribution to this ancient cosmic dialogue of artifacts. We now know that we are, however unconsciously, participating in a tradition that may be as old as the galaxy itself. 3I divided by Atlas has given us no answers about its creators. It has offered no technology, no wisdom, no warning. Its true gift is something far more precious and profound. It has given us a mirror. In its silent, alien, and reflective surface, we see not a glimpse of them, but a true and staggering vision of ourselves. We see our own youth. We see our profound isolation not as a curse, but as a stage of cosmic development. And we see the immense unspoken responsibility we now carry, the responsibility to be good ancestors, to ensure our own chapter in this grand narrative is one worth reading. The quest for discovery continues, as it always must. But we no longer step out into an empty void. We step into a hall of echoes. We explore a landscape rich with the memory of those who came before. And with a new and solemn reverence, we continue our own journey, not just as explorers, but as inheritors, ready to write our own verse in the great, silent poem of the cosmos.